Hi, this is the third lecture in the acetal series, and what I want to go over now is a problem that students in the past have always had difficulty with, which is when you have a carbonyl and you are asked to react with a diol like this in the presence of acid. Students often have difficulty coming up with the product, okay? And if you look at the other reactions that you are able to do, this problem is really not that different, all right? So let's take a look at the one that I made for the 3x5 card. So here's the carbonyl and here's the alcohol, right? So this carbon of the carbonyl, this oxygen leaves eventually as water, and in its place you have 2 moles of alcohol in its place. So 2 of the hydrogens from 2 moles of alcohol leaves as water, H2O, and then in its place the OR group is attached to this carbon, and you have this product, which is the carbon of the carbonyl. It's got the O2 OR groups, okay? The only difference between this problem and this problem is that the alcohols are attached to each other, all right? So you could imagine that when you draw the hemiacetal, it will look like this, right? Where one of them has added. Now, because it's linked together, so they're stuck together in the second step, when the acetal actually forms, you know that this leaves as water, and instead of having another mole of alcohol coming, this serves as the second mole, so that it forms, it kind of wraps around, and then this oxygen is attached to that carbonyl carbon, all right? So I made a model of this again. I think it helps with a lot of students to see the molecule. So here's my carbonyl, oxygen, acetal, and here's my diol that are attached together, right? So these 2 oxygen of the diol is going to be what is attached to this carbon of the carbonyl. So I'm going to just take this off. And imagine this leaving as water with 2 hydrogens here, and then the hydrogen, so I took off the 2 hydrogens from the alcohol, and then I'm adding the 2 oxygen. Notice they're stuck together still, and this is the product that you get. And then the 2 hydrogen that I took off from the alcohol will go here, and that is leaving as water, H2O, right? So this is what I have drawn here. So if you follow this same mechanism, you'll see that the chemistry stays exactly the same. It's just kind of throwing you off with this alcohol that's a diol, right? Now, in this reaction we talked about last time about the reversibleness of this. So if you add a lot of water to this and react with the acetal, then you're forcing the reaction to go backwards, if you will, because you're favoring the equilibrium going back. Then you isolate the starting material, which is the carbonyl and the alcohol, all right? So that's called hydrolysis. Which is what I want to briefly look at. So hydrolysis is just a reverse of acetal formation. So you're going backwards. So in this problem, for example, if I'm going from acetal back to ketone, then the hydrolysis reagent that I need is water and acid for all hydrolysis of acetals, okay? If you're going forward, going from carbonyl to the acetal, then you need the whatever alcohol plus acid. Those are the two different reagents that you would need depending on which way you want to go. So at this point, you should be able to do problems like this. Give hydrolysis product of the following molecule with an acid catalyst. So you want to basically zoom in on the acetal carbon. This is an important carbon. And so here and here. And when you go backwards, that's the carbon that becomes the acetal by O, as in here. And then you get the alcohol back. And you should also, after doing these problems, you should be able to do 20.12 and 20.26a. All right. Now I'm going to continue on. I'm not sure whether I'm going to have time or not, but I want to continue on with the concept of protecting group. Remember in the first lecture, I talked about why acetal chemistry is important, and one of the reasons was sugar, but the other was what I said was protecting group. All right. So as the name says, protecting group is basically serves to protect a functional group, just like the name says. All right. So this is best illustrated by looking at a reaction. So I have this as a starting material, and I want to make this. So I want to go from A to B. All right. So look at the transformation. Notice that the carbonyl stays exactly the same, and notice that this ester functional group is now have become an alcohol. All right. So what kind of transformation is that? This is oxidation level 3, this carbon, right? 1, 2, 3, and this oxidation level is 1. So this is a reduction problem. All right. So remember, I want to go from oxidation level 3 to oxidation level 1. What does that mean? Then I have to use a strong reducing agent, correct? But if I use strong reducing agent, what will happen to the carbonyl, which is at the oxidation level 2, right? So remember, the strong reducing agent will reduce the oxidation level 3 carbon to 1, but in that process, it will also reduce 2 to 1 as well. So if I just took LAH and took this and reacted, then I would get, instead of the desired, what I want, I will get reduced here and a reduction here. So I will get this diol as a product, but I don't want that. I want just this. All right. So this is where the protecting group comes along to help us to be able to do this. All right. So this is a scheme that this chemist would follow, in which this, because we don't want anything to happen to that, we would do a protection step. All right. And we would convert it to acetal from a ketone. And then we are using the reducing agent, lithium aluminum hydride. And notice that it does not do anything to the acetal. It stays intact. And it only reduces the ester to alcohol. So then after we do the reduction, we deprotect by doing a hydrolysis of the acetal. So we're now happy with what the transformation we've done, and now we want the carbonyl back. Then we do the backward reaction, which is hydrolysis, which is lots of water with acid, and you get the carbonyl back. Okay, so acetal is used as a as the ketone functional group protector. All right, and that's what protecting groups do. They protect the functional group. And how does it do that? It's because acetals are essentially ethers. And you know from Chem 114 that ethers are inert to bases, reducing, oxidizing agents. They're inert to Grignard, nucleophiles, etc., but reacts in presence of acid. All right, so as long as you're not doing reaction in an acidic condition, it will stay in acetal form, and you do the chemistry that you need to do, and then voila, you take it off, and then you have the product that you desired. All right, so a lot of the chemistry that we need to do involves this protection, deprotection type of chemistry, and I'm going to give you, because I got 1 minute left, one little example. You don't have to write this down. I just want to show you something that I used in research a while ago. This is a steroid, and I needed to do chemistry at this alcohol, but not do chemistry at this carbonyl. All right, so what I did was, first I protected as an acetal group, and then I oxidized the alcohol to an aldehyde, and now I have a differentiation of this carbonyl versus this carbonyl, right? And I only wanted to do chemistry here, and I had to do Grignard or whatever, I forget now, but basically I did a nucleophilic reaction at this carbonyl. And if I didn't do this protection step, then it would react at both places, and I didn't want it to do that. All right, so that's a piece directly from my research in the past. All right, so now you should be able to do these problems, whether it's hydrolysis. So look at the reagents, and is it a forward reaction where you're making an acetal like in here, or is it a hydrolysis reaction? And you should be able to give me the products in this. And this is a synthesis reaction in which you may or may not have to use protecting group to do the synthesis. So you're going to have to figure that out on your own. And then lastly, you should be able to do problem 20.11 from your textbook. All right, so that concludes this lecture.